Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are taking a deep dive into atomic spectra from Unit 12, atoms. We'll simplify this complex-looking topic so you can really understand the quantum rules behind light and color and make sure this concept is crystal clear for your board exams. Okay, let's start with something you see every day. Think about a sodium street lamp. Why does it glow only in that very specific yellow-orange light? Or a neon sign, why is it specifically red? Why don't they just glow white, like a simple incandescent bulb with a full rainbow of colors?
That's a good question. I always just assumed it was because the gas inside is really hot, maybe. Doesn't everything glow when it gets hot enough?
You would think so, and that's a very logical thought. But here's the surprising part, which is also a key point for your exams. A gas discharge tube, like a neon sign, can actually be quite cool to the touch, and yet it produces these vivid, specific colors. The color depends on the element's identity, sodium, neon, whatever is inside, not just the temperature. The temperature might change the brightness, but not the actual color.
Yeah.
So what is happening inside the atom to cause this?
So the color is like a fingerprint of the atom itself. What's going on inside that's so selective? Why only certain colors and not others?
Exactly. And that question takes us right out of classical physics and into the quantum world. The core idea is that atoms don't emit light continuously, like water flowing from a tap. Instead, they emit light in very specific, discrete packets. This means they only produce light at certain specific wavelengths. This unique pattern of bright lines is what we call the atomic line spectrum. And yes, it's the chemical fingerprint for every single element. But to understand why, we have to look at the huge problem classical physics had. According to Rutherford's model, electrons orbit the nucleus.
Right, but if they're orbiting in a circle, they're always accelerating, changing direction.
Precisely. And classical theory says any accelerating charge must radiate energy. So if the electron is constantly losing energy, it should spiral right into the nucleus. Calculations showed that an atom should collapse in, something like 10 to the power of -8 seconds? But, atoms are stable. Matter exists. So the old rules were clearly wrong. We needed new rules. And this is where Niels Bohr comes in with the idea of quantization. Let's use an analogy to build a mental picture. Think of an atom like a circular staircase. The nucleus is at the center, on the ground. The electrons are like people on the stairs. They can only stand on level 1, level 2, level 3, and so on. They can't just float between the steps. That idea, that only certain levels are allowed, is quantization. It's not a smooth ramp. It's a set of fixed, rigid steps.
Okay, so quantization means fixed steps. I get that. But if an electron is on level 1, the lowest step, what stops it from just falling off that step and radiating energy?
That is the genius of Bohr's idea. He proposed that an electron on the lowest possible level, which we call the ground state, simply cannot radiate energy and fall further.
Why not?
Because there's no level 0 to fall into. The staircase has a bottom step. The atom is stable because the electron is already in its lowest allowed energy state. The problem of atomic collapse is just solved. Now, when energy is added, say, from an electric current in a neon sign, the electron gets a kick. It absorbs that energy and jumps up the staircase to a higher level, let's say from level 1 to level 3.
Okay, so it gets excited.
Right. But it doesn't stay there. It's unstable. So it immediately wants to fall back down to a lower, more stable level. And when it falls, it releases that exact energy difference between the steps as a single packet of light, a photon.
Ah, and since the steps are at fixed heights, the energy differences are also fixed.
Exactly. And that is why we only see those specific colors. Any color corresponds to a specific jump between two specific steps on that atomic staircase.
Okay, now that we have the mental picture, let's see how Ensert formalizes this with Bohr's famous postulates. These are really the foundation of the chapter. Could you read out the 3 key points Bohr proposed?
Sure. It says, an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. These are called the stationary states. 2, the angular momentum L of the orbiting electron is quantized, meaning it is some integral multiple of h divided by 2 pi, so L equals nh over 2 pi. And 3, when an electron makes a transition from a higher energy state, EI, to a lower energy state, EF, a photon is emitted having energy equal to the difference, h nu equals AI minus EF. Fantastic. So you see, the first postulate solves the stability problem we just talked about. The third one explains where the photon, the spectral line, comes from. But the real key, the mathematical heart of the model, is that second postulate, the quantization of angular momentum. This idea that L can only be h2 or 2h2 or 3h2, it seems a bit strange, a bit arbitrary, doesn't it?
Yeah, it does. Why that specific formula?
Well, Bohr didn't know why at the time, but he saw that it worked. He combined this quantum rule with classical physics. the Coulomb force providing the centripetal force. And from that, he derived that only certain energies are allowed. He got the famous formula, n equals minus 13.6 electron volts divided by n squared. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. So because only those specific energies, n, are allowed, the energy differences, delta E, are also very specific. And that is why we only see specific wavelengths of light, since lambda equals hc over delta E. Let's take a quick example. The most famous line in hydrogen spectrum is the red one, called H-alpha. It's produced when an electron falls from the N-3 level down to the N-2 level.
Okay, so we need the energies. Using the formula, the energy for n equals 3 is minus 1.51 eV, and for n equals 2, it's minus 3.4 eV.
Correct. So what's the energy difference? What's the energy of the photon that gets emitted?
It would do the difference between them. So minus 1.51 minus 3.4. That's
Okay.
1.89 eV.
Exactly. 1.89 electron volts. Now, that's a tiny amount of energy, but when you plug that value into the formula, lambda equals EHE,
You get a specific wavelength.
you get a specific wavelength of 656 nanometers. And that corresponds almost perfectly to the exact shade of red light that scientists have been observing for decades in hydrogen gas tubes. The theory perfectly matched the experiment. It was a massive breakthrough. This whole structure also explained why the spectral lines are organized into these predictable families, or series. It all depends on which step the electron lands on.
So all the jumps that land on level 2 are one family, and all the jumps that land on level 1 are another.
Precisely. All transitions that end at NF8-1 form the Lyman series. These are big jumps, so they release a lot of energy. High energy means ultraviolet light, which we can't see. The transitions that end at NF2 form the Balmer series. These are smaller jumps, and their energies fall right in the visible light spectrum. That's the red, the cyan, and the violet lines we see. And jumps ending at NF3, the Passion series, are even smaller energy and fall in the infrared. Now, before we move on, let's go back to that point about Bohr's second postulate, L exceeds NH2. Even Bohr felt it was a bit of an arbitrary trick just to make the math work. But about 10 years later, de Broglie provided the deep theoretical reason for it. And it connects beautifully to our next topics. He realized the electron isn't just a particle. It's also a wave.
A wave. How does that explain the fixed orbits?
Think of a guitar string. It can only vibrate in stable patterns, right? Harmonics. For the electron wave to be stable in its orbit, the circumference of the orbit must fit an exact whole number of its wavelengths.
Ah, so if it doesn't fit perfectly, the wave would interfere with itself and cancel out.
It would destroy itself. Exactly. The only stable orbits, the stationary states, are the ones that are standing waves. And when you do the math, that standing wave condition is mathematically identical to Bohr's quantization of angular momentum. It wasn't a trick. It was a consequence of the electron's wave nature. Okay, with that deep physics understood, let's focus on two silent killers, common misconceptions that can cost you marks in the exam. First, students often think Bohr's model works for all atoms. This is wrong. Bohr's simple equations work only for hydrogen and hydrogenic atoms.
What's a hydrogenic atom?
An atom or ion with only a single electron, like singly ionized helium, He plus 1, or doubly ionized lithium, Li2 plus Win. The moment you have two or more electrons, the model fails.
Why does it fail?
Because Bohr's math only considers the force between one nucleus and one electron. It completely ignores the complicated repulsive forces between multiple electrons. For that, you need much more advanced quantum mechanics.
Okay, so for an exam question, if it's about neutral helium, I have to remember Bohr's formulas don't apply, only if it's He plus. That's a good trap to know.
Precisely. Now, the second mistake. Students see the red H-alpha line, the cyan H-beta line, and so on, and they think those different colors come from different elements mixed in the tube.
Oh, I can see why they'd think that. Different colors, different sources.
Exactly, but it's wrong. All those lines, red, cyan, violet, are produced by the same element, hydrogen. They just come from different electron jumps happening inside different hydrogen atoms in the tube. A jump from N3 to Ne2 gives red. A bigger jump from N4 to Ne2 gives cyan. An even bigger jump from N5 to Ne2 gives violet. So remember this, one element, many possible transitions, equals many spectral lines.
One element, many lines. Got it.
Good. Now, to help all this stick, let's lock in some memory anchors. First, for the spectral series, remember the mnemonics, LB, PBP. That's Lyman, Balmer, Paschen, Brackett, P-Fund, in that order. Lyman ends at 1, Balmer at 2, Paschen at 3, and so on. Remember, Balmer is the one you can see. Second, always remember this powerful phrase. Line spectra are atomic fingerprints. It perfectly captures the idea that they are unique to each element because the energy levels, the staircase steps, are unique. And finally, a physical gesture. I know it sounds silly, but try it. Stand up and pretend to climb a staircase. Feel the solid steps under your feet. Now try to stand between two steps. You can't, right? You'll fall. That feeling of only being able to stand on the steps, that is quantization. Electrons take the stairs, they never slide down a ramp. All right, to summarize this entire deep dive, here are 3 exam-safe factual points you absolutely must know. 1. Atomic spectra are not continuous. They consist of discrete lines, which is direct proof that the energy levels inside an atom are quantized. 2. Bohr's model explained this by postulating that angular momentum is quantized, L equals nh over 2 pi. This rule directly leads to the formula for the specific allowed energy levels and solves the problem of atomic collapse. And 3. The spectral lines are organized into series. The visible Balmer series, which is the most important for your practicals, comes from any electron transition that ends on the second energy level, n final equals 2. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is PROF Sam.
Yes, ProfSam.com. Keep studying hard, and we'll see you for our next concept explainer.